Good afternoon. It is 1:19 p.m. on March 19th, 2019. This is a little discussion on Newton's second law. I'm going to bring up my PowerPoint slides so you can see what we're talking about. Newton's second law, and just I'm going to give a little tiny lecture on the PowerPoints and then I'm going to diverge to an experiment. So start with Newton's second law. Newton's second law is that a force causes an object to accelerate. The acceleration is directly proportional to the force acting on the object and is inversely proportional to the mass. Now, Newton didn't quite write it that way. He actually didn't give the inversely proportional to the mass. He basically said that the constant of proportionality, force is proportional to, acceleration is proportional to force, and the constant of proportionality is 1 over the mass. So the direction, that's pretty much how Newton stated it in Principia Mathematica. The other thing that you need to pay attention to is the direction of the force is the same as the direction of the acceleration, or the acceleration is the same as the direction of the force. So if I apply a force to my cart, then it's going to accelerate in the direction of the applied force, of the applied net force, and that's very important. So this is stated here in the second slide, that if I have an object that is subjected to forces F1 through Fn, then the amount of acceleration the object is going to experience is directly proportional to the sum of the forces F1 through Fn. And that constant of proportionality, again, is going to be 1 over the mass. Keep in mind that this force F net is actually F1 plus F2 plus F3, and it is a vector sum. Okay, not a numerical, but a vector sum. And the acceleration points in the same direction as the net force vector. Now, I'm going to show you a little experiment. PowerPoint, and I'm going to go to Word. And here is Word. In this case, this is a Vernier experiment of force versus acceleration. So we have a cart, and as you can see, here's my setup. I have a cart with a force sensor attached to it. In this case, the force sensor is Dyson. And I'm going to accelerate this cart and see how we can determine the force, or how we can determine the acceleration from the force. So the objective of the demonstration is to collect force and acceleration, compare the force versus time and acceleration versus time graphs, and analyze a graph of force versus acceleration to determine the relationship between force, mass, and acceleration. So this is my experiment, and here you have my demonstration. I'll get rid of this, and I am going to first bring up a Logger Pro sheet. So this is new. Okay, so here's my new sheet, and I'm going to get rid of my my LabQuest because I don't need it right now. What I do need is Dyson, and Dyson is already connected. Now I'm going to zero this out. Now the procedure is, for this experiment, is what I'm going to do is I have the cart with a hook on it. And what I'm going to do is I'm going to accelerate the cart through a short distance, and I'm going to compare the force versus acceleration data on this motion. So let me go ahead and set that up. The cart is currently at 58 centimeters on my track, and I'm going to go to 48 centimeters. So the first thing I have to do is I'm going to have to weigh the cart, because I'm going to have to figure out what I expect. So what I'm going to do now is pick up the cart. So I'll start taking data. And I'll pick up the cart. Heavy cart. I'll set it down. Sorry about that. and we're done. So you can see that the data was collected, and I'm not that interested in the ends, meaning here and here. I'm more interested in this middle section. So I will take a measurement of that. Now that should actually be the weight of the cart. So if I take that and I do an average, my cart is at 632 newtons. My cart is at 60.32 newtons as far as the mean goes. So I'm going to save this run as weight run. Okay. So there's my store. So there's my run. And I'll hide the data set right now because I don't need it. Now, we expect the cart to have a weight. And I'm just going to bring up my sheet because I calculated this out ahead of time. The cart has a weight of 179 grams. That's for the force sensor, and 512 grams for the cart itself, bringing us to a total of 691 grams or 0.691 kilograms. Giving that, I expect a weight by multiplying it by gravity as 0.691 times 9.81, which gives me 6.77 kilograms meters per second squared. So this is actually a Newton, and I remind you that if we, assuming Newton's second law is true, F equals ma, the unit of mass is the kilogram. The unit of acceleration is meters per square second. So the unit of Newton, 1 Newton, is equal to 1 kilogram meters per second squared. So we actually have Newtons here. We theoretically assume, based on the numbers that I have from previous measurements, that this is 691 grams, giving us a weight of 6.77 kilograms per meter per square second, or 6.77 newtons. That's what we measured is 6.32 newtons. So the difference is about 7%. I'm not going to cry over that. And the uncertainty is about 0.229 kilogram meters per square second. The mean of this is going to be, between the theoretical and the measured, is 6.54 newtons. So now let's go ahead and we're going to get some measurements for this experiment and see if we can come up with anything that makes any sense. Assuming Newton's law is true, we should get, for the graphs, the same type of graphs for the acceleration and the force. We should also get a straight line if we plot one versus the other. So we're going to do that now. And so I have my device. I'm going to zero my force sensor as planned. And there we go. And so now, again, going from 58, there we go, it's in the center, to 48. I'll go ahead and collect data. Start with the first. Okay, there's my data, and this I'll call run 1. And if you look at the graphs, we're already starting to see the constant of proportionality show up, that these graphs are proportional to one another. They peak at the same places, roughly. They have troughs in the same place. So we've got a good data set here. So now what I'm going to do is I'm going to create a page. So I'll just add a page, and I'm going to put a graph in there. Insert a graph. And on the x-axis, I am going to have, instead of time, I'm going to have x acceleration. And I'm going to get rid of the connections so that you can see more to the point of this. So there we go. And now just blow it up. Auto range. Here is my force versus acceleration. And if I did do a data curve, force is y, acceleration is x. If I go ahead and do the linear fit on this data, you can see everything fits in there. And here's my first data point, 0.6708. Let's blow this up a little bit so you can see it. So I'm going to keep this run, and I'm going to go into another one. Because that's the thing with an experiment. We have to do it multiple times. It's not good enough to do it just one. So I'm going to hide my data. And now I'm going to go back to page 1. And let's see if I can make this better. Sorry for doing this in the tape, but I figured it's probably better that you see it. So here we go. Data run number 2. We start at 58, we go to 48. We shake it up until we'll zero out the sensors just to make sure that everything works. And ready, set. Grab the hook and go. All right, there we are. I stopped too soon, as you can see. So what I'm going to do is I'm actually going to strike through that data. I don't want it. I don't want it. I'm going to stay from here to here and just get rid of it. And it gets rid of it in both graphs, which is kind of cool. Again, we see the same peaks, same shape of the peaks, same troughs, located in the same place all the time. So now I'll go to page 2. Page 2, again, I get the same graph, this linear graph. And so now what I'm going to do is I am going to, again, take a linear fit. .678. So this is run 2. I'm going to go ahead and save this. So it's already saved. Hide the data and do one more run. All right, reset. We're just about ready to go. Zero this guy out. Okay, so now one more run. And collect. Here we go. And looks like a good run. So I'll save it. And now let's find out what's going on here. So if I look again at page 2 where I have my force versus acceleration graph, once again you get a cloud of data points. Some are above, some are below. If I do a linear fit, .671. So there's my data. Now I'm going to go ahead and bring up my calculation sheet. We expected about 6.54. We got the following. we got 0.671. And if I look at the other two, so what did I get? For 671, 669, and 678. So there we go, 671, 669, 678. So there's my 3 data points. And so now, for each of these slopes, so now my expectation is that I should get about 0.691. I'm actually getting, let's do the average. Okay, that's what you get when you don't type it correctly. Mean data slope, 0.672. So I expected 0.691. I got 0.672. Let's take a look at the error. Okay, 0.5. .7% error. So I can say with confidence that the mass of this device is 0.691 kilograms. I can say that with a plus or minus 2% confidence. 2% confidence.